Right now, somewhere off the western coast of Norway, a car pulls onto a ferry, the engine shuts off, and the driver waits. 40 minutes to cross a body of water less than 5 kilometers wide. This happens 7 times on a single highway. The E39, Norway's most important coastal road, stretches 1,100 kilometers from Kristiansand in the south to Trondheim in the north, connecting cities that produce 60% of the country's export value. And yet driving it takes 21 hours because the road simply stops at the edge of 7 fjords and asks you to float across on a boat. Norway, one of the wealthiest and most technologically advanced nations on Earth, still moves its people and cargo the same way it did 100 years ago. That is about to change. The Norwegian government has approved a $47 billion plan.
This is the final crossing. The problem is clear, but so is the solution. Change is coming.
To eliminate every single ferry crossing on the E39 and replace them with engineering structures that have never been built before anywhere in the world. Floating bridges that sit on water 550 meters deep. Submerged tunnels that hang suspended inside the ocean itself, anchored by cables dropping into a black abyss over a kilometer below. And the longest, deepest subsea road tunnel ever attempted, bored through solid rock 392 meters beneath the surface of the North Sea. This is not a proposal. Construction has already started, and when it is finished, the 21-hour journey will take 11. To understand why this project is so extreme, you need to understand what a fjord actually is. A fjord is not a river, it is not a lake. It is a drowned glacial valley, carved over millions of years by ice sheets grinding through bedrock, leaving behind narrow corridors of ocean water that plunge to extraordinary depths. The Sognefjord, Norway's largest, is over 1,200 meters deep. That is deeper than the average depth of the Mediterranean Sea. The Boknafjord near Stavanger opens directly into the North Sea and is battered by Atlantic storms year-round. The Bjornafjorden south of Bergen is 550 meters deep and exposed to brutal crosswinds that can shut down marine traffic for days. These are not gentle bodies of water. These are vertical-walled oceanic trenches carved into the living rock of a continent, and the E39 has to cross every single one of them. Traditional engineering cannot solve this. You cannot sink bridge pillars to the bottom of a fjord that is a kilometer deep. You cannot bore a conventional tunnel through rock at that depth without astronomical cost and catastrophic pressure. And you cannot keep running ferries forever, because every ferry crossing adds 30 to 45 minutes of dead time, burns diesel fuel, emits carbon, and cripples the economic integration of an entire coastline. Norway needs something that has never been built, and so they are building it. The first problem they are solving is the Boknafjord.
At over 300 meters below sea level, this tunnel will be the deepest road passage in the world. We face unprecedented engineering challenges daily.
And they are solving it with brute force. The Rogfast tunnel is already under construction. When it opens, it will be the longest and deepest subsea road tunnel on Earth, stretching 27 kilometers beneath the Boknafjord and Kvitsøyfjord, reaching a maximum depth of 392 meters below sea level. To put that in perspective, the current record holder, the Ryfast tunnel, also in Norway, reaches 292 meters. Rogfast goes 100 meters deeper. The tunnel connects Randaberg near Stavanger to the island of Bakken, with a 4.1-kilometer spur tunnel extending to Kvitsøy Island. Parliament approved the project in 2017. Construction began in January 2018. Progress was halted in 2019 when costs overran the original budget of 16.8 billion Norwegian kroner. After a comprehensive review, the government reapproved the project with a revised budget of 24.8 billion kroner, roughly 2.2 billion US dollars, funded through a split of government allocation and toll-based loans. 70% of the construction is being handled by Implenia Norge and a joint venture with Stangeland Maskin. Skanska was awarded an additional 5 billion kroner contract for the northern section in 2022. Inside the mountain, tunnel boring machines and drill and blast crews are grinding through ancient Norwegian bedrock, advancing meter by meter through granite and gains. The blasted rock is hauled out on conveyors, the tunnel walls are lined with reinforced concrete, ventilation shafts are drilled upward to the surface, and emergency cross passages are cut between the twin tubes every 250 meters. 392 meters below the ocean floor, the water pressure above is immense. and the rock itself weeps moisture that must be continuously pumped and channeled away. The engineering is not exotic. It is relentless, grinding, industrial-scale patience. Every blasted face must be inspected for fracture propagation. Every concrete pour must cure under controlled temperature to prevent cracking at depth. Every ventilation system must be capable of clearing smoke from a vehicle fire within minutes, because at 27 kilometers, there is no quick way out. The Rogfast Tunnel is expected to open around 2033. When it does, the ferry crossing it replaces will simply cease to exist. But Rogfast is the conventional part. The crossings that make engineers lose sleep are farther north, where the fjords are too wide for tunnels and too deep for pillars. The Bjørnafjorden, south of Bergen, is the first of these impossible crossings.
Look at it. Miles of water, nothing but cliffs. They call this a problem. I call it an impossible equation.
5 kilometers wide, 550 meters deep, exposed to North Sea storm systems that drive 6-meter swells and sustained crosswinds exceeding hurricane force. No bridge has ever been built over water this deep, with no possibility of touching the bottom. The solution is a floating bridge, and it will be the longest ever constructed. The Bjørnafjorden floating bridge will be a curved, pontoon-supported highway stretching approximately 5 kilometers across the fjord. It will rest on 38 massive rectangular concrete pontoons, each roughly 50 meters long, floating on the surface of the fjord. 3 of these pontoons will be anchored to the seabed by mooring cables. The rest will float freely, held in alignment by the structural continuity of the bridge deck above and the tension of the mooring system below. The bridge curves. This is not aesthetic. A curved bridge deflects crosswind loads more efficiently than a straight one, preventing the structure from acting as a sail. The cable-stayed section in the center rises high enough to provide 150 feet of vertical clearance for cruise ships and cargo vessels passing beneath. The engineering challenges are staggering. Each pontoon must be fabricated in a coastal dry dock, a massive concrete casting operation involving thousands of tons of reinforced concrete per unit. The pontoons are then floated out to the fjord and positioned with centimeter-level precision using GPS-guided tugboats and anchor-handling vessels. The mooring cables descend into 550 meters of dark water, anchored to the fjord floor, using techniques borrowed from offshore oil rig installation, an industry Norway happens to lead the world in. Wave loading, current forces, tidal variation, wind shear, temperature expansion, fatigue cycling from millions of wave impacts per year, all of this must be modeled, tested, and survived for a design life of 100 years. The bridge's curved deck will use a combination of passive galvanic cathodic protection and specialized anti-corrosion coatings to fight the relentless salt assault of the North Sea. If it is built, and the Norwegian Public Roads Administration has already selected a design, this single structure will redefine what is considered possible in bridge engineering worldwide.
Standing here, amidst this impossible achievement, we are ready to take the next extreme step in engineering. This is just the beginning.
Now we arrive at the crossing that no one has solved before, the Sognefjord, 3,700 meters wide at its narrowest point, 1,200 meters deep. This is Norway's deepest, longest, and most iconic fjord. It is also a major shipping lane for military vessels and cruise liners. You cannot bridge it conventionally. A suspension bridge spanning 3.7 kilometers would require towers taller than any structure in Scandinavia and anchor points on a seabed that is over a kilometer down. You cannot tunnel under it. Boring through rock at 1,200 meters of depth beneath an active ocean floor would cost more than the entire rest of the E39 project combined, and you cannot skip it, because without crossing the Sognefjord, the highway remains broken. The proposed solution is a submerged floating tunnel, also called an Archimedes Bridge, and nothing like it has ever been built anywhere on Earth. The concept is deceptively simple. 2 concrete tubes, each carrying one direction of traffic, are submerged horizontally in the fjord at a depth of approximately 20 to 30 meters below the surface. They are too deep to be affected by surface waves, wind, or weather. They are too shallow to face the crushing pressure of the deep fjord below. The tubes have negative buoyancy, meaning they are slightly heavier than water and would sink if left alone. To prevent this, a series of approximately 15 floating pontoons on the surface are connected to the tubes by rigid vertical columns or tension cables, holding the tunnel at its precise depth. The pontoons are spaced and designed to allow full shipping traffic to pass between them on the surface. Inside the tunnel, drivers would experience something that looks remarkably like any modern subsea tunnel. 2 lanes, emergency exits, ventilation, lighting, except for the faint blue-green glow from small observation ports showing dark fjord water on all sides. The tubes are anchored to bedrock only at the entry and exit portals on each shore, where they transition from underwater structure to conventional mountain tunnel. The engineering unknowns are significant. How does a 4-kilometer hollow concrete tube respond to deep ocean currents pushing on it sideways? What happens if one or more surface pontoons are destroyed by a ship collision? How do you inspect and maintain the underside of a tunnel suspended in 500-meter deep water? Norwegian engineers have studied these questions using data from the offshore oil industry, and their models suggest the tunnel could withstand the loss of multiple pontoons without structural failure. Safety routes built into the twin-tube design would allow evacuation from one tube to the other in an emergency. But until the first one is built, submerged floating tunnels remain the most ambitious, untested infrastructure concept in modern engineering. The EMPRA has not yet decided whether the Sognefjord will definitely receive a floating tunnel, or whether a combination of extreme span suspension bridge and floating pontoon bridge might be used instead. Both options are being studied. Both would break world records.
The submerged floating tunnel represents a radical shift in engineering, redefining connectivity in Norway. We are at the forefront of this new era.
Beyond these 3 marquee crossings, the E39 project includes dozens of additional conventional tunnels, rock-cut road sections, and bridge upgrades along the entire 1,100-kilometer route. Each section must be designed for the specific local conditions of its fjord, its mountain pass, or its coastal exposure. Wind and wave measurement stations have been installed at every major crossing point, collecting years of environmental data to feed into structural models. Laser welding technology is being developed specifically for this project, a method that uses dramatically less energy than traditional welding, reduces carbon footprint, and enables automated precision fabrication of bridge components on-site near the fjords rather than shipping them from distant factories. The NEMPRA has already tested this technology on a pedestrian bridge, then a small road bridge, then a larger road bridge, progressively scaling up toward the massive Bjørnafjorden crossing. The goal is not just to build these structures, but to invent the construction methods that make them possible at this scale and cost. The politics of this project are as complex as the engineering. The total estimated cost ranges between 40 and 50 billion US dollars, making the E39 upgrade the most expensive infrastructure project in Norwegian history. Parliament has approved the vision, and the Rogfast tunnel is funded and under construction. But the more experimental crossings, the floating bridge, the submerged tunnel, face ongoing political debate. Critics argue that improved ferry services could achieve similar travel time reductions at a fraction of the cost. Environmental groups point out that a highway expansion designed to speed up car traffic conflicts with Norway's official climate policy of zero growth in urban car traffic. The Norwegian Green Party has called for scaling back the project. The ENPRA counters that the western coast generates 60% of national export value, and that reliable, weather-independent transport infrastructure is an economic necessity, not a luxury. The project's timeline has already stretched. The original ambition was full completion by 2038. Current estimates suggest the last crossing may not open until 2050 or beyond, depending on political priorities and funding cycles. But the direction is set. The Rogfast tunnel boring machines are already underground. The Bjørnafjorden bridge design has been selected. The Sognefjord studies continue. When this highway is finished, a driver in Kristiansand will start the engine, pull onto the E39, and drive north. No ferry, no waiting. 1,100 kilometers of continuous road, passing over bridges that float on the surface of fjords deeper than most oceans, through tunnels suspended inside the water column itself, beneath rock nearly 400 meters under the seafloor. The journey will take 11 hours instead of 21. Freight costs along the coast will drop by an estimated 50%. Cities that today feel isolated by geography will become neighbors connected by concrete, steel, and cables. And the fjords, those ancient scars left by glaciers grinding through a continent, will still be there, dark, deep, and indifferent. But for the first time in geological history, something will stretch across them that does not float on the surface and wait for the weather to clear. Norway is not building a road. Norway is building proof that geography is not permanent.
This bridge, this highway, represents years of hard work. Now, we finally connect this landscape forever. It's truly earned.